the homework you also have to think of. And so if you have some missing homework assignments, you can still get credit for those turning in at the end of the semester. All right, what I want to do today then is finish up chapter 15. And so this is the next part, you know. The next part is what happens, you know, if you heat. Let's say if I had a solid, liquid, or gas, what happens if I, you know, heat this up? Heat, you know, is usually given by this little triangle here. So if I heat this up, what's going to happen? Solid, or liquid, or gas. And so when we heat something up, two things could potentially happen. The two things are, it just gets hot. Or the other thing is, it changes states. That is, there's a phase change. And if there's a phase change, there's, you know, no delta T. Delta T is equal to 0, delta T being temperature. Here, delta T is greater than 0. And so what the heat can do is it can just go into warming up the solid or the liquid or the gas, so there's more kinetic energy. But at certain points, what happens is all that heat goes into breaking apart the solid, breaking apart the liquid, or breaking apart the gas when we convert it to plasma. And so that would be a phase change. Phase change is an example. A solid would melt. You know, a liquid would boil. A gas could go into plasmas, but we're not going to talk about that. If the object gets hot, then we could have, you know, a hot solid. So that results, or a hot liquid that results. So what determines which of these two things happen? Is it going to be the first one? It's just going to get hot, or is it the second one? What determines, you know, one or two is the temperature. The temperature is, if it's at the melting point is the temperature at which it melts, at which solid melts. So the T at which the solid melts, then we're going to have melting occur. All that energy is going into melting, and none of that energy is going into making it hot. If at the boiling point, dP, then we're going to have boiling occur. Boiling, you know, and so when we have melting or boiling, the temperature stays constant. So an easy way to visualize this is by using a heating or cooling curve. Now, since we're talking about heating, we call it the heating curve, but the cooling curve looks exactly the same, like this. And so look at a heating curve here. And the heating curve is just going to map out the temperature and the energy here in the form of heat. Heat is given a symbol, Q, little q, or big Q, depends. The Q is the symbol for heat. And so what we'll do is we'll just start off with a solid, a very cold solid here. And what's going to happen is this cold solid, it could be all the way to 0 Kelvin. You could do it. But let's say it would be very difficult to bring a solid that cold. So let's just say it's a cold solid, and what's going to happen? Well, as you add heat, so we're going this way, we're going to add heat to a solid. The solid should get hot. As the solid gets hot, the temperature increases. But can you increase the temperature of a solid up to infinity? Is that going to happen? No. Eventually, what's going to happen? It's going to get so hot, it's going to melt. And so you can't just, or decompose, but let's say it doesn't decompose, it just gets hotter and hotter. Eventually you hit a temperature at which it starts melting. That temperature is the melting point, MP. And so that's what we see here in this. So the solid just gets hotter and hotter until it hits this temperature. This temperature we're going to call the MP, the melting point. Okay, now as we add in the energy, the solid no longer gets hotter. What happens is all that energy goes into breaking apart that solid. In other words, melting the solid. And so what we'll see here is the temperature stays constant, but we're still adding heat. As we're adding heat, the solid continues to melt until all of it's melted. Once all of the solid has melted, then we have liquid. And so here I'll just write S for solid. Here I'm going to write S to L for solid melting into liquid, and then here it's all liquid. So if it's all liquid, what's going to happen is we add heat to a liquid. The liquid's going to get hot. Okay, can we add an infinite amount of heat to the liquid? No, eventually what's going to happen is we continue to add heat to the liquid. It's going to, eventually it's going to hit a point where it starts to boil. And that point where it starts to boil is called the boiling point here. We saw we had the normal boiling point. Does anybody remember the definition for the normal boiling point? It's the temperature at which liquid boils under normal atmospheric pressure. But the liquid can boil at different temperatures, depending on what the atmospheric pressure of the day is. It could be hotter or cooler. So for example, if the pressure is lower, the liquid boils at a lower temperature than it's normal. If the pressure is higher, then it boils at a higher temperature than normal. And so here we're going to hit the boiling point, whatever that is. And then once we hit the boiling point, the liquid gets hot enough to start boiling. And so all the energy goes into boiling the liquid. Here. And so this is the liquid. Solid warms, we'll say it. Here. And then here we have the solid melts. Over here the liquid warms. And then here the liquid boils. So we're going from liquid to gas, and we have boils. Eventually we're going to boil all the liquid. So all the energy is going into breaking apart the liquid, and then once we run out of liquid and there's no more liquid to boil, and we're just left with gas. If we're just left with gas and we add in energy, then the gas is going to get hot. And so the gas warms with the heat. And so this is the heating curve. Now the heating curve, we don't have to start off with a liquid or solid or gas. We could start anywhere here and then just follow the progression. In fact, we could go forward. If we go forward, it's heating. If we go reverse, it's cooling. All the temperatures will be the same, and the amounts of heat will be the same. It's just going backwards in this. Now, there are two equations that we use for this. The two equations are this. When an object gets hot or cold, the object being a solid, liquid, or gas. So the object, solid, liquid, or gas. Warms or cools. Then we use this equation. Q is equal to the amount times C times delta T. The amount is usually in grams, and so typically this is the mass grams. If it's the mass, then we'll just say MC delta T. MC delta T. So this is the equation that people remember. But it doesn't have to be grams. We could have moles or whatever else. Put that there. And C can be in different units. Okay, so the amount of heat depends on how many grams. The more grams, the more heat. The amount of heat depends on the temperature change. The bigger the temperature change, the more heat. The smaller the temperature change, the less heat. And the amount of heat depends on C. Now what is C? C is called the specific heat in this case. C equals the specific heat. It's also called the heat capacity. We already have experience with heat capacities. Some things can hold a lot of heat, some things can't. Things that can hold a lot of heat have high heat capacities, like water. Have you know, when you try to boil water, how long does it take to boil water? It takes so long to boil a pot of water. You got a gallon of water you're trying to boil, you got to give it, what, 15 minutes or something. Why? Because it's got a very high heat capacity. It has the ability to hold a lot of heat. Whereas if you want a hot frying pan, does it take 15 minutes to warm up a frying pan? No. Iron has a much lower heat capacity. Heat capacity or specific heat. And so it's the amount of heat that it takes to warm up an object. And so let's take a look at some numbers for specific heat here. Usually we find these in a data table. So I'm going to fast forward here. Oops. There. And let's look at some specific heats. What has the highest specific heat that you can see? The largest number. The largest number is the species that's going to hold the most heat. You see what has the largest? Aluminum? Okay, what is aluminum specific heat? 0.90. That looks, out of all the elements, that looks like the, oh wait, magnesium. Magnesium's a little higher. Out of the elements, but you know, we're looking at all substances, including compounds and mixtures, like concrete would be a mixture, 0.88. But the highest one I would see would be for the for water, liquid water. Liquid water has a very high specific heat, or very high heat capacity. That means it serves as an excellent heat reservoir. You can dump a lot of heat into water. This is why they use water to quench things, that is, cool things down. Because water is used anyway, it has a very high heat capacity, specific heat in the liquid form. In the solid form, it's a little less. Let's see. In the gaseous form, it's less as well, about half as much. The water is very high. Methanol is pretty high, 2.53. So these are good. What's very low are the metals. When you look at this, what has the lowest? Gold. Gold doesn't have much. In other words, gold is very good at heating up. If you heat up gold, it doesn't take much energy to warm it up. Whereas if you're heating up water, it takes a lot of energy to warm it up. And so the specific heat is given by these units here. And so let's just take a look at the highest specific heat on the table. The highest is water, and that's in the liquid form at 4.18 joules per gram degree C. And the way we read this is like this. For every gram of water, it takes 4.18 joules of heat to warm it up by 1 degree C. So if I had 2 grams of water, it'd take twice as much. 3 grams would take 3 times as much. If I want to double the temperature increase, I'd take double the energy. Triple the temperature increase, triple the energy. Okay, that goes for cooling as well, you know, except we gotta lose the energy rather than input the energy. And so if you want to cool down water, you gotta remove that energy by refrigeration or whatever else. It's a lot of energy to remove. Gold has the lowest. Gold takes barely any energy. It only takes 0.15 joules of energy to warm up a gram of gold by 1 degree C. That's nothing. So it's very easy to warm up gold. very difficult to warm up water. Those are the specific heats. All right, so an object warms or cools. This is the equation that we use. We use this equation here. What if there's a phase change, like it boils or whatnot? If there's a phase change, then we use a different equation for that. So what is the equation that we use for phase change? Show it here. Okay. Well, this is not the generic equation. Let me write it here. So actually, on this chart, let's take a look here. If the solid warms here, then the equation we use is Q is equal to mc delta T. If the liquid warms, then the equation we use is Q equals mc delta T. If the gas warms, the equation we use is Q equals mc delta T. The only difference is the C here. This would be the specific heat for the solid. This would be the specific heat for the liquid. This is the specific heat for the gas. So for example, water, this would be about 2. This would be about 4. This would be about 2. Okay. And then the temperature change. How big of a temperature change do you want? All right, now when we're dealing with the phase change like melting or boiling, then we're going to use something else, a different equation. Let's see, where was that curve here? And so for phase change, this would be, these are the phase changes that we have. We're going to have melting, boiling. In the reverse process, the reverse process of boiling is called condensation. And the reverse process of melting is called freezing. Melting has another name. You know the other name for melting? The other name for melting is called fusion, and it's confusing because fusion, usually when you fuse things together, you're thinking you're going to make a solid or something like that, or fusing it rather than breaking it apart. So fusion has the connotation that you're making something, not breaking something. Melting, you're breaking it, so fusion's for breaking it here. This fusion is different than the fusion you see in nuclear reactors. In nuclear reactors, you're putting things together like the sun. The sun is a gigantic nuclear reactor, and it's fusing hydrogens together to make helium. You know, this is not the same fusion, and so it's a bit confusing here, but we've got to use it, unfortunately. And so the heat, the amount of heat is equal to the amount times delta H of the phase change. And so we have different delta H's. And those are usually indicated by the subscript that we use. We'll have delta H of fusion, delta H of freezing, delta H of boiling, delta H of condensation. We only need one of the fusion or the freezing because the other is going to be equal and opposite. There's something called the first law of thermodynamics. The first law of thermodynamics says that energy is neither created nor destroyed. That was back in chapter 1. And so the amount of energy that's required to melt is the exact same amount of energy that we have to remove to freeze it. And so it's just opposite. The opposite, we just change the sign. So let's take a look at some of these here. Okay, so we look at this and then we just take a look. These are the delta H's fusion here. This is delta H is of vaporization. So here's melting, the amount of energy it requires to melt. Which one requires the most energy to melt? Sodium chloride. Sodium chloride at 519 joules for every gram. That means the bonds are pretty strong in sodium chloride. It makes it hard to melt. Which one is weakest? Which one's the easiest? Mercury. Mercury is a very interesting one because mercury is already melted at room temperature. The other one, lead. Lead, only 23. The bonds are pretty weak. Lead and mercury. In fact, lead, you know, if you rub lead metal, you can rub some lead onto your skin. You want to be careful handling lead metal. Lead. Okay, so the highest delta H of fusion is sodium chloride. Where's water? Here's water. And so to melt ice requires 333, which is not bad, you know, quite a bit of energy. Okay, now let's take a look at vaporization. Vaporization is boiling. Let's say that. Yeah, that makes sense. Vaporization. Just right in here. Vaporization. Same thing as boiling. So this is the delta H of boiling. This is the amount of heat it requires to boil a gram. And so which one is the highest? Which one requires the most heat to boil? Aluminum. Looks like aluminum is pretty up there. Which is the lowest? Mercury. Mercury is not that volatile though. None of these are very volatile. So for example, the most volatile one would probably be out of all these water. Well, water, you know, this when we read this chart, it's a bit deceptive. Because we have to think, what is a liquid at room temperature? And so when we're thinking about liquids, there's mercury and water. All these others are solids. So comparing these numbers isn't a fair thing to do. We can compare solids with solids, but we should compare liquids with liquids. If we compare liquids with liquids, and if we had a bigger chart here, what we'd see is that water has a pretty high heat of vaporization. Water takes up a lot of energy to boil. Liquid water has some interesting properties in that sense, which means these interesting properties are absolutely required for life. So this is why they're looking for water, evidence of water on other planets. Let's see. Of course, there could be other, life forms not based on water, but for us, it's water. And so the only one example we're really going to worry about is water. Water requires 333 joules of energy, or kilojoules, actually. Is that joules or kilojoules? Kilojoules. Oh, then I have it wrong.
For the fusion.
Fusion. Yeah, sorry. This would be, let's do this, sorry, one more time here. We want to look at H2O for fusion, H2O solid. And so the delta H of fusion is 333 joules per gram. So for every gram, it takes 333 joules of energy to melt it. So if we look at H2O liquid, delta H of vaporization is 2.26 kilojoules per gram. That is 2,260 kilojoules per gram, which would be 2,260,000 joules per gram. And so compare the two energies. To melt water, 333 joules. To vaporize liquid water, 2 million joules. Huge difference. huge difference is because to melt the water, the hydrogen bonds can still stay intact, you know, because the waters are still touching each other. But to vaporize the water, you have to completely break the hydrogen bonds that hold the water molecules together. And so that's going to cost quite a bit more energy. And so this is striking as far as the amount of energy goes. Okay, otherwise we don't need to know, we don't have to memorize any of these numbers here.
Wouldn't it just be 2260? How did you go from 2.26 kilojoules to 2260 kilojoules?
Oh, because I made a mistake. Sorry. 2.26. You're right. This would be 2,260. What am I doing? Joules. I did one extra step. Not 2 million. But still, this is a significant jump here. Going here. So it's a significant jump up in energy. Is that right? Yeah. Yeah, so sorry. Good catch though. All right, so when we have melting, what equation do we use? We use Q is equal to the amount. Now the amount is in mass, so we're just going to say M times delta H. We just got to make sure the units cancel, because sometimes people do it in moles for the amount as well. Rather, sometimes it's just easier to do it in mole. And so here, Q is equal to M times delta H. There's no delta T here. Why is there no delta T? There's no delta T here. The reason there's no delta T is because when you melt it, it melts at 0 degrees C, the temperature doesn't change. When you boil water, it boils at 100 degrees C, the temperature doesn't change. And so the temperature is constant. So over here, we see it. When we melt ice, it melts at 0 degrees C. When we boil water, it boils at 100 degrees C. There's no temperature, there's no delta T, it's just one temperature. So the temperature doesn't show up here. We have to consult the table to figure out what the temperature is at the melting point and what the temperature is at the boiling point. Consult the table. Okay, so let's take a look at some example problems like this one. How much energy is needed to vaporize 188 grams of a liquid if its heat of vaporization is 1.13 kilojoules per gram? And so what we want to do is we want to vaporize. If we have a liquid and we're vaporizing it, then we're just here on this step. We're going across this horizontal arc here. We're going from liquid to gas, which is vaporization. And so the equation we use is Q is equal to the mass times delta H. So we have the mass here times delta H. The mass is 180 grams times delta H, 1.13 kilojoules per gram. The grams cancel and leaves us with kilojoules. 212 kilojoules. So what we're doing here is we're starting with a liquid here, and we're going to boil the whole thing. Boiling the whole thing is going to take 212 kilojoules. So we start off at 0 kilojoules added at the beginning, and then we end here at 212 kilojoules, and we vaporize the entire sample of liquid. And so over here we have 188 grams of liquid. By the time we get to this side, we have 188 grams of gas, no liquid. And as we traverse this, we're getting less liquid and more gas. Eventually, we'll have all gas here. That. And so, like halfway, we can figure it out. Halfway, we have half the liquid remaining, and we've converted the other half into gas. How much energy is required to melt 25.0 grams of ice at 0 degrees C? So this is the same kind of thing. over here, we start off here, we're melting ice, so solid to liquid. We start off with 25 grams of solid ice, 0 grams of liquid water. And as we traverse this, we want to end up with 0 grams of solid ice and 25 grams of liquid water. And so, how much energy? Well, that's a change of state. Melting is Q is equal to the amount times delta H. So the amount is 25 grams, delta H is 333 joules per gram. You don't have to memorize that number, by the way. So it's going to be given. And so Q is equal to amount times delta H. Grams cancel. 8.33. 8,330 joules, or 8.33 kilojoules. So to traverse this entire thing will cost us 8.33 kilojoules, and then we'll melt that entire sample of ice. How much energy is required to change the temperature of 25 grams of water from 10 degrees C to 50 degrees C? So we have to figure out, water at 10 degrees C, is it a solid, liquid, or gas? Yeah, it's a liquid, and so that puts us here. It doesn't put us at 0, we're above that, so it puts us around here, 10 degrees C. So our starting point is a liquid at 10 degrees C here. And then we want to warm it to 50 degrees C. At 50 degrees C, what is water? Solid, liquid, or gas? Liquid. And so we're just going to warm up the liquid. And so we're going to go from a liquid at 10 degrees C to a liquid at 50 degrees C. So the equation that we use is Q is equal to MC delta T. Q is equal to MC delta T. And so M is the mass, which is 25 grams. C is the specific heat of water. We looked that up in a table. A lot of people have it memorized. So it's 4.18 joules per gram degree C. The specific heat, actually a lot of people have water's specific heat memorized in calories. Do you know how many calories it takes to heat up a gram of water? By a degree C? 1. In fact, that's how the calorie is defined. The calorie is defined as the amount of energy required to heat 1 gram of water by 1 degree C at around 4 degrees Celsius. And so, 1 calorie is the same as 4.18 joules, so that's where this number comes from. So this is why a lot of people know this one. And it's pretty high. This is what we call pretty high specific heat, because when compared to all the other things we saw, it's much higher. So that's our C. So we have mass times C times delta T. Delta T is T final. The final temperature is 50 minus T initial. Initial temperature is 10. And so delta T is plus 40. Plus 40 would be a temperature increase. A negative 40 would be a temperature decrease. So the order is important. We could have a positive, which is an increase, or a negative, which is a decrease. And so plugging in the numbers and looking at the units, all the units should cancel except for joules. And that gives us 4.18 kilojoules of energy. And so starting here and ending here, 4.18 kilojoules. Okay, let's look at the next example here. Calculate the total heat transfer when 19.6 grams of ice, initially at minus 12 degrees C, is heated to steam at 115 degrees C. So they tell us we're starting off with ice at minus 12 degrees C. So this is ice at 0 degrees C, so ice at minus 12 degrees C will be here. And then we're going to heat it. So as we heat it, what's going to happen to the ice? We're going to heat it all the way to steam at 115. So this would be steam at 100 degrees C here. So 115 is going to end here. So we want to start here and then end here. If we start here, the first thing that's got to happen is the ice warms up to 0 degrees C. The ice warms up to 0 degrees C. Well, each section has its own equation. And so what we'll do is we'll take the first segment and then do that calculation. So we'll call that step 1. So we'll call this Q1. And what we have to do is we have to sum up all the Q's. So if we're going to heat the ice, we can't heat ice all the way to 115 degrees C. Something's going to happen before that. In fact, well before that. Because what's going to happen is the ice has got to warm. And so ice warms. The ice warms from minus 12 degrees C to 0 degrees C. 0 degrees C is the maximum temperature that we can have ice at. And so what equation do we use for that? Q1 is equal to, it's going to equal to M C delta T. And so what's the mass? 19.6 grams. What's C? Well, C's, you got to look that up or it's given. And so let's go look it up. Do you see it? Yeah. 2.06. So times 2.06, the units? Joules per gram degrees Celsius. And so here the grams cancel. The only thing left to cancel is degrees Celsius. If we got to cancel degrees Celsius, we need T final minus T initial, or delta T. So what is T final? What is T initial? And so what this is going to come out to is it's going to be 19.6 times 2.06 joules per degree C times, this is going to be plus 12 degrees C. Plus 12 degrees C means it's warming. So the degrees C cancels. And so for the first segment, what do we have? How much energy will it take to warm up the ice? And so 19.6 times 2.06 times 12. And so this is going to cost us 484.5 joules. So if I look at this, starting from here and ending here, I'm going to have 485 joules roughly. So that's about 485 joules. Okay, once I warm up the ice to 0 degrees C, as I add additional heat, the ice is not going to get hotter. What's going to happen at 0 degrees C is the ice is going to melt. And so I'll just continue adding heat. We're going to call this segment Q2. And so for Q2, we'll just continue adding heat until all the ice melts. And so here I start off with 19.6 grams of ice, no water. At the end here, I'm going to have 0 grams of ice, 19.6 grams of water. So we're going to melt all that ice here. So how much heat will that take? Well, let me erase this here. So this is going to be for the second segment, Q2. The equation is going to be the amount, which is in mass in this case. So it's going to be M the amount times what? Delta H. Since we're melting it, we call this delta H of fusion. We have to look that up. So let's look up delta H of fusion for water. And do you see it? Yeah. And so the amount is 19.6 grams of solid ice times the delta H of fusion, which is 333 joules per gram of ice melted. So the grams cancel, and that leaves us with joules. So let's see what we get here for the second segment. That's 19.6 times 333. 6,526.8. 6,526.8 joules. So the first segment here cost us 485 joules. The next one to melt is going to cost us quite a bit of energy here. Even though the temperature doesn't change, we've got to break a lot of those hydrogen bonding interactions. So this comes out to about 6,500 joules. This is just about, we're going to do more precise calculation later when we add it up. And so this is about 500 joules, this is about 6,500 joules. No. Okay, now once we have 19.6 grams of liquid water, we're done melting it. And so that liquid water is going to warm from 0 degrees C, and we're going to call that Q3. And so how hot can the water get? So Q3, here, Q2 was, we're going to take 19.6 grams of ice and convert that to 19.6 grams of water, H2O liquid. This is ice at 0 degrees C, and we're going to have each 19.6 grams of H2O liquid at 0 degrees C. So the temperature doesn't change here. Again, all the energy is is being used to melt. But once it's all melted, then that energy can be used to increase the temperature. And so Q3, we're going to have 19.6 grams of H2O liquid at 0 degrees C. And what we're going to do is we're going to warm that to 19.6 grams of H2O liquid at, what's the maximum temperature for H2O liquid? At 100 degrees C. And so the equation here is going to be the amount, which is going to be mass, times C times delta T. And we have MC delta T for this. All right, so the amount is 19.6 grams. We need the specific heat for liquid water. You might have it memorized, but if not, it's going to be given. What is the specific heat of liquid water? It's big. Yeah, it's 4.18 joules per gram degrees C. So the grams cancel. And then the amount of heat is going to depend on how hot we're getting it. And so there's going to be T final. T final is going to be 100 degrees C minus T initial, 0 degrees C. So it's plus 100 degrees C. So the degree C cancels, and that leaves us with joules. So let's see. It's out to 19.6 times 4.18 times 100. 8,192.8. 8,192.8 joules. So the next segment here, Q3, is going to cost us about 8,200 joules. 8,200 joules. Go here. So far, that's gonna cost us the most energy, is warming up that water. Didn't cost that much to melt it. Didn't cost that much to heat up a block of ice. All right, once all the liquid has warmed to 100 degrees C, then we can't get it hotter than 100 under normal pressures. It's not going to go hotter than 100. And so what we'll do here is we're going to go to the next step, which will be Q4. The next segment here, Q4, is we're going to take our 19.6 grams of liquid water and then boil it. So here are 19.6 grams of H2O liquid at 100 degrees C. And if we try to add more energy, then it's going to start to boil a little bit at a time. So eventually, once we boil it all, we're going to end up with 19.6 grams of H2O gas at 100 degrees C. And so Q4 is going to, well, it's a phase change, so it's equal to the amount. For us, it's mass times delta H. So 19.6 grams, it doesn't change. We're not losing any or gaining any. 19.6 grams. And then delta H. This delta H is, what's it called? Delta H vaporization. Delta H vaporization. Let's see what the delta H vaporization is. What is delta H of vaporization here? 2.26 kilojoules per gram. The grams cancel out. .6 times 2.26. 44.296. 44.296 kilojoules, which would be 44,296 joules. So this next segment here is going to cost us about 44,000 joules. 44,000 joules. So far, what's cost the most energy? Yeah, boiling. So my X, I need to redo the X scale here. It's all screwed up. This should have been the longest here. Quite a bit longer than the other. So this takes a lot of energy to boil that. Okay, once we've boiled all of it, then we're on the last segment here, which is Q5. Q5, we have the no more liquid remains. We have 0 grams of liquid water. We have 19.6 grams of steam. Q5. We're going to take that 19.6 grams of H2O gas at 100 degrees C and then warm it to how hot do they want it? 115. So we'll end up with 19.6 grams of H2O gas at 115 degrees C. The hotter we get it, the more energy it's going to take, but we can figure out how much energy it takes is by MC delta T, the temperature change. And so the mass is 19.6 grams. C, okay, what is C? I have to go to the other table for that. Do you see what it is? Yeah, it's going to be 2.00 the unit.
Joules per gram or Celsius.
Yeah, joules per gram degrees C. Our delta T is T final, which is 115 degrees C, minus T initial, which is 100 degrees C. So what does that come out to? This is going to come out to joules, what we want. This is going to be 19.6 times 200 times plus 15. 58,800 joules. Is that right? 58,000? Oh, no. Divided by 100. 588 joules. And so the last little bit is going to cost us 588, about 600 joules. And so what we have to do is we're starting here and ending here, so what we'll have to do is sum up all of these. So that's about 500. 500 plus 6,500 is about 7,000. 7,000 plus 8,000 is going to be about 15,000. 15,000 plus 44 is going to be about 59,000. And then about 60,000 joules altogether to traverse this whole thing. So let's take a look at the final stuff. So they did it segments, you know, I just call it Q1, Q2, Q3, Q4, and Q5. And just add them up. It should be about 60,000. $60,000 joules would be about 60 kilojoules. Just add up the segments. I use more, you know, digits here. 485.485. 6,530. I did 6,000. I forgot the numbers. I erased them, unfortunately. But we'll just add up the numbers here and get that. All right. What happens if we go backwards? What happens if we go backwards is it's going to cost us negative. If we reverse this process, it's going to be negative 60.1. And where do the negatives come? The negatives come from this, you know. Yeah, the delta H of condensation is the negative of the delta H of vaporization. It's the same amount of energy, it's reversed. Delta H of freezing is the negative of delta H of fusion. And so we just change the sign on those because we have to remove the heat rather than add the heat. And that's all. The delta T's are going to be reversed. So the delta T is, T final is 100, T initial is minus 150, so it's going to come out negative 15 degrees C rather than positive 15 degrees C. And so everything is going to come out negative, positive, if we were to go backwards. All right, any questions on that? I did the scale. My scale is all screwed up. This scale looks a little bit better. What took the most energy? What took the most energy was this step here. So they made this a little bit longer than the other. Ours should have been about 4 times longer than the other. So this is still a little small. This looks like about double the amount of energy. We had about quadruple the amount of energy. So this is a very long, time-consuming step here to boil the water. Hold it. Oh, this is why, you know, steam, it takes a lot of energy to boil. That means it takes a lot of energy to condense. And steam burns are some of the worst burns you can get because there's a huge amount of energy involved in condensation as well as vaporization. And so steam burns versus liquid water burns are like 4 times more energy. 4 times more energy means 4 times more burn, basically. So if you had 100, what would you rather have? You know, would you rather have a pound of water at 100 degrees C, or a pound of steam at 100 degrees C burn you? Well, a pound of water would be a lot better. Neither would be the best. All right, that's chapter 16, 15. Now we're on to chapter 16. Chapter 16 deals with solutions. And so we're going to go through this kind of quickly. 16, 17, 18, some of the final chapters. What we'll do right now is take a break and then we'll start 16.